There's something you should know about our planet. Every 100,000 years or so, Earth undergoes a transformation so complete, it's hard to believe we're talking about the same world. Ice expands from the polar regions. Glaciers push across entire continents. Oceans retreat as water locks itself into frozen sheets miles thick. Climate zones compress toward the tropics. Then, with almost the same reliability, it reverses. The ice melts back. Warmth returns. Forests reclaim land that spent millennia under frozen darkness. This has repeated itself again and again, stretching back through geological time. The rhythm is so consistent you'd think someone planned it. Except the rhythm isn't perfect. It's close. Remarkably close. But there are irregularities. Moments when the ice should have surged forward but hesitated. Periods when warming should have arrived but delayed. Times when the pattern stutters just enough to make you realise we don't understand everything, and that's the unsettling part. If you're here trying to fall asleep, you're in the right place. That's why these exist. Consider subscribing and dropping a comment about your location and the current time where you are. I read through them, and it's genuinely interesting. People from all over, drifting off at different hours, all thinking about the same frozen mysteries. The ice ages themselves aren't disputed. We have proof stacked in layers of Antarctic ice, preserved in sediments from ocean depths, carved into bedrock by glaciers that vanished 10,000 years ago. The evidence surrounds us. We've even identified some causes. Earth's orbital path changes over time. The planet's axis shifts and wobbles. Its tilt varies slightly across millennia. These movements alter how sunlight reaches different latitudes. They generate cycles, measurable patterns in solar radiation hitting Earth's surface. But there's a gap in the explanation. Those orbital variations alone don't account for what we observe. The calculations fall short. Earth's wobbling orbit should trigger temperature swings of perhaps a degree or two. What we actually get are full ice ages, glacial periods where ice blankets half of North America. Climate transformations so severe that species either adapt, relocate across thousands of miles, or disappear entirely. Something is amplifying the signal, taking these small astronomical nudges and turning them into planetary upheaval. The question at the heart of this story is deceptively simple. Why does Earth freeze every 100,000 years? What mechanism drives this relentless cycle? What force is powerful enough to lock half the planet in ice for millennia, then release it just as thoroughly? Scientists have been chasing this mystery for over a century. What they've discovered is both elegant and terrifying. A story written in ice cores drilled from Antarctica, in ocean sediments pulled from the deepest trenches, in the very bones of mountains scraped smooth by, glaciers long since melted. The answer involves orbital mechanics, atmospheric chemistry, ocean currents, and feedback loops that amplify small changes into catastrophic transformations. It involves mathematics so precise you could predict ice ages thousands of years in advance. It involves chaos so complex that tiny variations cascade into completely different climate states. It's a detective story spanning millions of years, solved by scientists who learn to read evidence invisible to the naked eye, who develop techniques to measure time and temperature and carbon dioxide concentrations from hundreds of thousands of years ago. But before we can understand the why, we need to understand the what. What exactly happens during an ice age? What does it mean for Earth to freeze? How do we know it happened at all? Because here's the thing. 150 years ago, nobody believed this story. Scientists laughed at the idea of ice ages, scoffed at the notion that ice sheets could cover continents. The evidence was everywhere, literally carved into the landscape, but it took decades for anyone to see it, to connect scattered observations into a coherent picture of planetary transformation. So let's start at the beginning. Not the beginning of ice ages themselves, which stretches back millions of years into deep time, but the beginning of our understanding, the moment when humans first realized that the world they inhabited was not permanent, not stable, not the unchanging stage for human drama that everyone assumed. The moment we discovered that Earth has a history, a violent, chaotic, frozen history that shaped everything we see around us. The Swiss Alps in the early 1800s, beautiful, majestic, carved by the hand of God into dramatic peaks and valleys, or so everyone believed. The mountains were eternal, unchanging monuments to divine creation. But there were oddities if you looked carefully. Huge boulders sitting in valleys, far from any cliff they could have, fallen from, composed of rock types that didn't match the surrounding geology. Deep scratches carved into solid bedrock in parallel lines, as if something enormous had scraped across the stone with tremendous force. Valleys with peculiar U-shaped cross-sections instead of the V-shape that rivers carve. Piles of mixed rock and debris, unsorted jumbles of everything from house-sized boulders to fine sand, scattered across landscapes in long ridges. Local people had names for these features. Erratic boulders transported by forces unknown. Moraines, ridges of debris marking boundaries nobody understood. Striations, mysterious scratches that ran for miles. But nobody had a good explanation for how they got there. The prevailing theory, such as it was, involved the biblical flood. Perhaps Noah's deluge had carried massive boulders and deposited them randomly. Perhaps the receding waters had carved the valleys and scratches. It was the best explanation available that fit within accepted, religious and scientific frameworks of the time. Then came a Swiss scientist named Louis Agassiz, born in 1807, brilliant, ambitious, unconventional in his thinking. He studied fish fossils initially, became an expert on glaciers almost by accident. In the 1830s, while doing fieldwork in the Alps, he noticed something that others had seen but not understood. The glaciers were moving, slowly, imperceptibly to casual observation, but definitely moving. He placed stakes on the ice and returned months later to find they'd shifted downhill. The ice was flowing like extremely slow rivers, pushed by its own weight, grinding against bedrock and valley walls. And here's what struck him. The scratches on bedrock near modern glaciers looked identical to scratches in valleys miles away, where no ice currently existed. The moraines at the edges of glaciers matched ridges far downstream in ice-free zones. The U-shaped valleys carved by active glaciers matched valleys throughout the Alps. What if, Agassiz wondered, those distant features weren't carved by floodwaters but by glaciers? What if ice had once extended far beyond its current limits? What if the entire region had been covered in ice? In 1837, Agassiz presented his theory to the Swiss Society of Natural Sciences. The reception was not warm. Scientists laughed. They dismissed the idea as absurd. Glaciers covering entire continents? Ridiculous. Ice ages? Impossible. The evidence Agassiz cited could be explained by floods, earthquakes, volcanic activity, anything except ice. His reputation suffered. Colleagues thought he'd lost his mind, wasted his considerable talents on a crackpot theory that contradicted both scripture and common sense. But Agassiz persisted. He studied glaciers obsessively. He even built a hut on the R Glacier and lived there for extended periods, measuring ice movement, documenting erosion, cataloguing the types of debris glaciers carried and deposited. He travelled throughout Europe looking for evidence of past glaciation, finding it everywhere once he knew what to look for. The same erratic boulders, the same scratched bedrock, the same distinctive landforms stretching across Scotland, Scandinavia, northern Germany, Russia. In 1840, he published his book Studies on Glaciers, laying out the comprehensive case for ice ages. He proposed that a great ice period had once gripped the northern hemisphere, that massive ice sheets had advanced from the polar regions, covering land as far south as the Mediterranean. It was a bold claim, a revolutionary claim, and it was mostly correct, though Agassiz got some details wrong, as pioneers inevitably do. He thought there had been one great ice age. We now know there have been many, cycling repeatedly over millions of years. The scientific community remained skeptical for decades, but gradually, as more researchers examined the evidence, as geologists mapped glacial features across continents, as the accumulation of data became overwhelming, opinions shifted. By the 1860s and 70s, Ice Age theory was gaining acceptance. By the early 1900s, it was established fact. The Earth had experienced ice ages, multiple ice ages. The evidence was undeniable once you learned to read it. Other scientists built on Agassiz's foundation. James Kroll, a Scottish scientist working as a janitor because formal employment in academia was denied to someone of his working-class background, developed the first astronomical theory of ice ages in the 1860s. Kroll proposed that changes in Earth's orbit and axial tilt could alter the amount and distribution of sunlight reaching the planet, potentially triggering ice ages. He was onto something profound, though he lacked the computational tools to fully develop the mathematics. That would come later, in the work of Serbian mathematician Milutin Milankovic. But we're getting ahead of ourselves. Before we can understand why ice ages happen, we need to understand how we know what we know. How do you study events that occurred hundreds of thousands of years ago? How do you reconstruct temperatures, ice extent, sea levels, atmospheric composition from times long before humans existed, let alone started keeping records? The answer involves some of the most ingenious scientific detective work ever accomplished. The evidence is everywhere, literally carved into the landscape, frozen in glacial ice, preserved in ocean sediments, recorded in the very chemistry of ancient air bubbles trapped in ice for hundreds of thousands of years. Learning to read this evidence transformed our understanding of Earth and time and climate. It revealed a planet far more dynamic, far more changeable, far less stable than anyone had imagined. A planet that freezes and thaws on timescales that dwarf human history. So let's examine that evidence. Let's see how scientists learned to read Earth's frozen past. How they discovered not just that ice ages happened, but when they happened, how severe they were. What caused them? What ended them? The story is written in ice and stone and the bones of the planet itself. You just have to know how to read it. The best climate records come from the most unlikely source. Ice. Not the ice from ancient glaciers that have long since melted, but ice that's still frozen, that's been accumulating layer upon layer for hundreds of thousands of years in places so cold it never fully melts, even during warm periods. Antarctica, Greenland, high mountain glaciers. These are Earth's freezers, preserving information about past climates with extraordinary detail and precision. When snow falls in Antarctica, it doesn't melt, it accumulates, layer after layer, year after year, century after century. The weight of newer snow compresses older layers into ice. Air bubbles get trapped between ice crystals, preserving samples of the ancient atmosphere. Dust particles settle on the surface before being buried, recording volcanic eruptions and continental dust. Storms. Chemical isotopes in the water molecules themselves record temperature at the time the snow formed. Each layer is a page in Earth's climate history. In the 1960s, scientists began drilling into these ice sheets, extracting cores that revealed climate going back thousands of years. The early cores were impressive, reaching back tens of thousands of years. But the real breakthrough came later, with deep drilling projects in Antarctica and Greenland that extracted ice cores going back hundreds of thousands of years. The longest ice core ever retrieved from Antarctica's Dome Sea reaches back 800,000 years. 800,000 years of continuous climate record preserved in frozen water. What these cores reveal is astonishing. By analysing the ratio of different oxygen isotopes in the ice, scientists can calculate temperature when that ice formed. Heavier oxygen isotopes require more energy to evaporate, so during cold periods, the ratio shifts in measurable ways. The technique is so precise you can reconstruct temperature changes of fractions of a degree. By measuring the composition of air bubbles trapped in the ice, you can determine atmospheric carbon dioxide and methane concentrations from hundreds of thousands of years ago. You can even measure dust levels, revealing how dry and windy the climate was. The ice cores show a clear pattern. For the past 800,000 years, Earth's climate has oscillated between cold glacial periods and warmer interglacial periods. The cycle is remarkably regular. Ice ages last roughly 100,000 years, then the climate warms rapidly within just a few thousand years. The warm interglacial periods last 10,000 to 15,000 years, then the slow descent back into ice begins, over and over, 8 complete cycles in the past 800,000 years, each one following the same general pattern, though with variations in timing and intensity. During glacial periods, temperatures in Antarctica were 8 to 12 degrees Celsius colder than today. Carbon dioxide levels dropped to around 180 parts per million, compared to about 280 parts per million during warm periods and over 420 parts per million today. The planet was a fundamentally different place: colder, drier, windier, less vegetation, lower sea levels, ice covering vast areas that are currently temperate or even tropical. But ice cores are just one source of evidence. Ocean sediments provide another incredibly detailed record, sometimes going back even further in time than ice cores. As tiny organisms called foraminifera live and die in the ocean, their shells sink to the seafloor, accumulating in layers. The chemistry of those shells records ocean temperature and ice volume. By drilling cores from the ocean floor and analysing the shells at different depths, you can reconstruct ocean conditions and global ice volume going back millions of years. The ocean sediment records confirm what ice cores show and extend it further back. The 100,000-year glacial cycle dominates for roughly the past million years. Before that, the pattern was different. Ice ages came and went on a roughly 41,000-year cycle. Something changed about 1 million years ago, shifting Earth from one pattern to another. Understanding that transition is one of the great unsolved puzzles in climate science. On land, the evidence is written in the landscape itself. Glacial valleys with their distinctive U-shaped profiles, carved by ice that ground away everything in its path. Striations on bedrock, scratches aligned in the direction the ice moved. Erratic boulders transported hundreds of miles from their source by glaciers, then deposited when the ice melted. Moraines marking the furthest extent of ice sheets, ridges of unsorted debris pushed to the edges like snowplows piling snow at the roadside. In the northern hemisphere, you can trace the maximum extent of the last ice age by following these features. Ice-covered Canada reached as far south as the Great Lakes, burying what's now New York, Chicago and Seattle under ice miles thick. In Europe, ice sheets covered Scandinavia, reached into northern Germany and Poland. Mountain glaciers in the Alps, the Himalayas, the Andes extended far beyond their current limits. Globally, about 30% of Earth's land surface was covered in ice at the peak of the last glacial period, compared to about 10% today. Sea levels during ice ages dropped dramatically because so much water was locked up in glaciers. At the peak of the last ice age, roughly 20,000 years ago, sea levels were about 120 metres lower than today. That's almost 400 feet. Coastlines looked completely different. You could walk from Asia to North America across the Bering Land Bridge. Britain was connected to continental Europe. Indonesia was part of the Asian mainland. The geography of the entire planet was transformed. Scientists can measure past sea levels by studying coral reefs and coastal features that formed at previous sea level positions, now submerged or elevated depending on whether they formed during high or low stands. They can date these features using radiometric techniques, building a timeline of how sea levels rose and fell in sync with ice ages. The correlation is exact. When ice sheets expand, sea levels drop. When ice melts, sea levels rise. The relationship is direct and measurable. All of this evidence points to the same conclusion. Earth's climate is not stable. It oscillates between states, frozen and warm, glacial and interglacial. The transitions are rapid on geological timescales, taking just a few thousand years. The pattern is regular enough to predict, but complex enough that small variations cascade into large differences. And here's the crucial part. We're living in one of the warm periods right now, the Holocene interglacial, which began about 11,700 years ago when the last ice age ended. Human civilization exists entirely within this warm window. Agriculture was invented during this interglacial. Cities were built. Writing developed. Everything we consider human progress happened during a period of unusual climate stability that represents perhaps 1/10 of the time span Earth has experienced over the past million years. We're living in the exception, not the rule. The normal state of Earth in recent geological time is significantly colder than what we're experiencing now. That raises profound questions. How long will this warm period last? Are we due for another ice age? Or have human activities altered the climate so dramatically that we've broken the cycle entirely? To answer those questions, we need to understand what causes ice ages in the first place. What force is powerful enough to freeze and thaw the planet on such regular timescales? The answer, it turns out, involves orbital mechanics, atmospheric chemistry, and feedback loops that amplify small changes into massive transformations. If you're still with me, still drifting towards sleep while contemplating ice sheets and geological time, good. That's exactly the vibe we're going for here. Cosmic timescales, planetary transformations, the deep comfort of knowing that Earth has survived far worse than anything happening today and will continue long after we're gone. If this resonates with you, consider subscribing. Tell me in the comments where you're listening from and what time it is. Are you in Alaska watching the Northern Lights? Melbourne at sunrise? Somewhere in between? The community that forms around these videos is genuinely wonderful. Now let's talk about orbits. Because the key to understanding ice ages comes from outer space, from the way Earth moves through space around the Sun, from variations so subtle you'd never notice them in a human lifetime, but so powerful over tens of thousands of years that they can freeze or thaw an entire planet. Earth's orbit around the Sun is not perfectly circular. It's an ellipse, slightly oval-shaped, meaning Earth's distance from the Sun varies throughout the year. Currently, Earth is closest to the Sun in early January, about 147 million kilometers away. By early July, we're at our farthest point, about 152 million kilometers distant. The difference is only about 3%, but it's enough to affect the amount of solar energy reaching Earth at different times of year. But here's what makes it interesting. That ellipse changes shape over time. Sometimes Earth's orbit is nearly circular, other times it's more elongated. The cycle takes about 100,000 years to complete, oscillating between more circular and more elliptical configurations. This variation is called eccentricity. When the orbit is more eccentric, the difference between closest and farthest approach to the Sun is greater, meaning seasonal differences in solar energy are more pronounced. Earth also wobbles on its axis like a spinning top that's starting to slow down. The axis traces a circular path in space, a motion called axial precession. This wobble takes about 26,000 years to complete one full cycle. It affects which hemisphere is tilted toward the Sun during different seasons. Currently, the northern hemisphere experiences winter when Earth is closest to the Sun, meaning northern winters are slightly milder than they would be otherwise. In about 13,000 years, that will reverse. Northern hemisphere winter will coincide with Earth's farthest distance from the Sun, making winters more severe. Additionally, the tilt of Earth's axis itself varies over a roughly 41,000-year cycle, oscillating between about 22.1 and 24.5 degrees. Currently, we're at about 23.5 degrees and decreasing. Greater tilt means more extreme seasons. Summers are hotter, winters colder, because each hemisphere leans more dramatically toward or away from the Sun during its respective summer and winter. Smaller tilt means milder seasons, less temperature difference between summer and winter. These three orbital variations, eccentricity, precession, and obliquity, were first calculated in detail by Serbian mathematician Milutin Milankovic in the 1920s and 30s. Working largely by hand with staggering mathematical complexity, Milankovic calculated how these orbital parameters varied over hundreds of thousands of years, and how they affected the amount and distribution of sunlight reaching Earth. His calculations showed that summer sunlight in high northern latitudes varied significantly due to these orbital changes, sometimes receiving substantially more solar energy, other times substantially less. Milankovic proposed that ice ages were triggered when high northern latitude summers received less sunlight. Here's the logic. Ice sheets primarily form in the northern hemisphere because that's where most of the land is concentrated. In the southern hemisphere, Antarctica is already covered in ice year-round, and most of the rest is ocean, which doesn't support permanent ice sheets. So northern hemisphere summer sunlight is crucial. If summers are cool, snow that falls during winter doesn't fully melt. It accumulates year after year. Eventually it compresses into glacial ice that begins to flow and expand. The theory was elegant and mathematically sophisticated. Milankovitch published his work in the 1920s and 30s, but it was largely ignored by the scientific community for decades. The calculations were difficult to verify without independent climate records going back hundreds of thousands of years. And there was a problem. The changes in solar energy caused by orbital variations are relatively small. Milankovitch calculated variations of perhaps 1 to 2 degrees Celsius in high latitude temperatures due to orbital effects alone. But ice ages involve global temperature drops of 4 to 7 degrees Celsius. The orbital forcing seemed too weak to explain the observed climate changes. Then, in the 1970s, the ice core and ocean sediment records became detailed enough to test Milankovitch's predictions. Scientists analysed the timing of ice ages from ocean sediments and compared it to the calculated variations in Earth's orbit. The correlation was striking. Ice ages occurred when Milankovitch's calculations predicted reduced summer sunlight in high northern latitudes. The timing matched too precisely to be coincidence. The dominant cycle in recent ice ages was roughly 100,000 years, matching the eccentricity cycle. Earlier ice ages followed the 41,000-year obliquity cycle. Milankovitch was vindicated. Orbital variations do drive ice ages. The astronomical theory was correct. But the amplification problem remained. How do small changes in orbital parameters create such dramatic climate shifts? The answer involves feedback loops, mechanisms that amplify the initial orbital forcing into much larger climate changes. Understanding these feedbacks is crucial to understanding why Earth freezes so thoroughly, and why the ice eventually retreats. The most important feedback involves ice itself. Ice is highly reflective. When sunlight hits white ice and snow, most of it bounces back into space rather than being absorbed as heat. Dark surfaces like soil, rock, and ocean water absorb sunlight and warm up. This is called the albedo effect, the measure of how reflective a surface is. Fresh snow can reflect up to 90% of incoming sunlight. Ocean water absorbs over 90%. Here's how the feedback works. Orbital variations reduce summer sunlight in high northern latitudes. Temperatures drop slightly. Snow that falls in winter doesn't entirely melt during summer. It accumulates. White snow covers dark ground and vegetation. The increased reflectivity causes more sunlight to bounce back into space, rather than warming the surface. This causes further cooling. More snow accumulates the following winter. More dark surface is covered with reflective white. The cooling accelerates. The ice spreads. Once ice sheets begin forming, they have their own dynamics that amplify growth. As ice accumulates and thickens, it flows outward under its own weight, spreading like extremely slow-motion pancake batter. The advancing ice kills vegetation, exposing more dark soil that then gets covered by reflective ice. The ice sheets alter atmospheric circulation patterns, creating high-pressure zones that suppress cloud formation, reducing greenhouse effect warming. The cooling becomes self-reinforcing, but ice albedo feedback alone doesn't fully explain the magnitude of ice age cooling. There's another crucial player, carbon dioxide, the greenhouse gas that traps heat in the atmosphere and warms the planet. Ice core measurements show that during glacial periods, atmospheric CO2 levels drop from about 280 parts per million during warm periods to roughly 180 parts per million during ice ages. That 100 parts per million decrease might not sound like much, but it has massive climate effects. Lower CO2 means less greenhouse warming. The planet cools further, reinforcing the ice expansion. But here's the puzzle. What causes CO2 levels to drop when ice ages begin? The answer involves ocean chemistry and circulation in ways scientists are still working to fully understand. The oceans contain about 50 times more carbon than the atmosphere. They act as a massive carbon reservoir, absorbing CO2 from the air or releasing it depending on conditions. Temperature affects how much CO2 water can hold. Cold water holds more dissolved gas than warm water. So as the planet cools, the oceans absorb more CO2 from the atmosphere, lowering atmospheric levels, further reducing greenhouse warming. Ocean circulation also plays a role. During glacial periods, circulation patterns change. The formation of sea ice in polar regions affects water density in deep ocean currents. These changes alter how much CO2 the ocean releases to the atmosphere versus how much it stores in the deep ocean. Additionally, changes in ocean biology affect CO2. Plankton and other marine organisms absorb CO2 and incorporate it into shells and tissues. When they die, they sink, carrying carbon to the deep ocean. Changes in ocean productivity and the efficiency of this biological pump affect atmospheric CO2 levels. The exact mechanisms linking ice ages to CO2 changes are still being researched. It's a complex interplay of ocean temperature, circulation, chemistry, and biology. But the correlation is clear from ice core records. When ice ages intensify, CO2 levels drop. When ice ages end and the planet warms, CO2 levels rise. The two are linked, though scientists debate whether CO2 changes drive ice ages or respond to them. The evidence suggests it's both. Orbital forcing initiates the cooling. Ice albedo feedback amplifies it. Declining CO2 levels amplify it further. All three work together, turning small orbital variations into planetary transformation. There are other feedbacks too. Vegetation changes affect climate. During ice ages, forests retreat toward the equator. Grasslands and tundra expand. Different vegetation has different albedo and different effects on atmospheric moisture and carbon cycling. Dust levels increase during glacial periods because the climate is drier and windier, exposing more bare soil. Dust in the atmosphere reflects sunlight and seeds cloud formation, both of which can cool the planet further. Methane levels, another greenhouse gas, also drop during ice ages, though for reasons not fully understood. All these feedbacks work together, amplifying the relatively weak orbital forcing into dramatic climate change. Small initial variations in solar energy trigger feedbacks that reinforce and accelerate the climate shift. The system has tipping points where feedbacks overwhelm initial forcing, driving rapid transitions between climate states. This explains why ice ages build slowly over tens of thousands of years, as orbital parameters gradually reduce summer sunlight, but end rapidly, within just a few thousand years, when orbital changes push the system past a threshold where warming feedbacks dominate. Understanding these feedbacks is crucial for another reason. They tell us that Earth's climate is not linearly responsive to forcing. Small changes can trigger large effects through reinforcing feedbacks. This has implications for modern climate change. Human CO2 emissions are pushing atmospheric levels far above anything seen in the past 800,000 years. We're conducting an experiment in feedback amplification, potentially triggering warming that exceeds the direct effect of the greenhouse gases we're adding to the atmosphere. But there's another mystery embedded in the Ice Age record that we haven't addressed yet. Why did the dominant cycle change from 41,000 years to 100,000 years about a million years ago? What caused that transition? Why do feedbacks amplify the 100,000-year eccentricity cycle in recent times, when earlier they amplified the 41,000-year tilt cycle? This question has puzzled scientists for decades, and the answer remains debated and uncertain. If you're still awake, still contemplating orbital, mechanics and climate feedbacks and planetary transformations, I'm impressed. This is genuinely complex science, the kind that took generations of brilliant researchers to figure out. But it's also deeply fascinating if you let yourself think about the implications. We're living on a planet with built-in climate variation driven by cosmic forces. Our comfortable modern world exists during a brief warm period between ice ages. That's both humbling and slightly terrifying. Before we move on, maybe drop a comment about where you're listening from and whether any of this is helping you sleep or keeping you awake thinking about ice sheets. I genuinely want to know. And if this kind of content works for you, subscribe so you don't miss future episodes. We do this regularly, diving deep into science and history and the kinds of questions that make you realize how little we truly understand about our own planet. Now let's talk about the transition, the moment roughly a million years ago when Earth's climate started dancing to a different rhythm, when the 41,000-year cycle gave way to the 100,000-year pattern we see today. Because understanding this transition might be key to understanding whether we're breaking the cycle with modern climate change. Ocean sediment records show clearly that before about 1.2 million years ago, ice ages followed a roughly 41,000-year pattern, synchronized with variations in Earth's axial tilt. The tilt cycle was the dominant driver. Ice sheets expanded and retreated in rhythm with changes in how much each hemisphere tilted toward or away from the sun during summer. But then, gradually over several 100,000 years, the pattern changed. The tilt cycle became less important. Ice ages started lasting longer, becoming more severe, following the 100,000-year eccentricity cycle instead. This transition is called the mid-Pleistocene transition, and it's one of the great unsolved puzzles in climate science. Why would the dominant forcing change? The orbital cycles themselves didn't change. Eccentricity, precession, and obliquity continued varying exactly as they always had. But Earth's climate response shifted from primarily responding to the 41,000-year tilt cycle to primarily responding to the 100,000-year eccentricity cycle. Something about Earth's climate system changed, though scientists hotly debate what. Several hypotheses have been proposed. One involves carbon dioxide. Perhaps long-term changes in volcanic activity or rock weathering or ocean chemistry gradually reduced background CO2 levels. With less greenhouse warming, the planet became more sensitive to small variations in solar forcing, allowing ice sheets to grow larger and persist longer. Once ice sheets reached a certain size, they became self-perpetuating through albedo feedback, locked in until orbital variations pushed the climate past a threshold where rapid melting could occur. Another hypothesis involves ice sheet dynamics. Perhaps changes in landscape or ocean circulation altered how ice sheets behaved. Before the transition, ice sheets may have been less stable, more prone to collapsing before reaching maximum size. After the transition, they became more stable, able to persist and grow larger over longer periods. This could involve changes in bedrock topography as earlier ice ages scoured the landscape, or changes in ocean currents that transport heat to polar regions and influence ice sheet edges. Some scientists propose that the build-up of thick regolith, the layer of loose rock and soil covering bedrock, may have played a role. Early ice ages ground bedrock into smaller particles, creating thicker regolith layers that insulated the ground beneath ice sheets, allowing ice to persist longer and grow thicker without melting from geothermal heat below. This is speculative, but potentially important. The honest answer is, we don't fully know why the transition occurred. Climate models can reproduce aspects of it, but no single mechanism fully explains the observations. It likely involves multiple factors working together. The climate system crossed some threshold where feedbacks began favouring longer, more intense ice ages rather than shorter, less severe ones. Understanding this transition matters because it tells us something fundamental about how feedbacks operate in Earth's climate system. It also raises unsettling questions about stability. If Earth's climate can shift from one dominant pattern to another over geological timescales, what prevents it from shifting again? Could modern changes push the system into a different regime entirely? Could we inadvertently trigger feedbacks that lock the climate into a new state, different from both ice ages and the warm interglacials we're familiar with? These aren't idle questions. Earth has experienced dramatically different climate states in the deeper past, before the current ice age cycles began, 3 million years ago before the Pleistocene ice 4. Ages started. Earth was significantly warmer with much less ice. Go back further, to 50 million years ago during the Eocene, and Earth was even warmer still, ice-free, with crocodiles living in the Arctic and palm trees in Antarctica. The planet is capable of radically different climate states. The current oscillation between glacial and interglacial periods is just one mode of operation, not the only possibility. What we've learned from studying ice ages is that Earth's climate has tipping points. Small changes can cascade into large effects through feedbacks. The system can shift from one stable state to another relatively rapidly. This is not reassuring when we consider modern climate change. We're adding greenhouse gases to the atmosphere at rates far faster than anything in the geological record, except for catastrophic events like asteroid impacts or massive volcanic eruptions. We don't know exactly where the tipping points are or what feedbacks we might trigger. Some scientists, worry about permafrost feedback. As the Arctic warms, permanently frozen ground begins thawing, releasing methane and CO2 that have been locked in frozen soil for thousands of years. This additional greenhouse gas release could accelerate warming beyond what our emissions alone would cause. Others worry about ice sheet collapse, particularly in West Antarctica and Greenland, where warming ocean waters undercut the edges of ice sheets, potentially triggering rapid collapse that would raise sea levels by meters. There are also potential cooling feedbacks that might counteract warming, though these are more speculative and less well understood. Increased cloud cover could reflect more sunlight. Enhanced rock weathering could draw down atmospheric CO2 over thousands of years. But these operate on much slower timescales than the warming we're causing, so they offer little comfort for the next century or two. The key lesson from studying the mid-Pleistocene transition is that climate is capable of changing its fundamental behaviour, of shifting from one regime to another, even when the external forcing doesn't change dramatically. This suggests we should be very cautious about assuming the climate will respond predictably to our emissions. We're pushing the system into territory it hasn't experienced in hundreds of thousands of years, possibly millions. The past may not be a reliable guide to the future when we're conducting an unprecedented experiment. One thing is clear from the geological record: ice ages eventually end. No matter how thick the ice grows, no matter how complete the freeze, Earth always warms again. Orbital variations eventually shift, bringing more summer sunlight to high latitudes. Feedbacks that reinforced cooling reverse, becoming warming feedbacks instead. Ice sheets begin melting at their edges. Albedo decreases as dark land is exposed. CO2 levels rise as warming oceans release dissolved gas. The warming accelerates, becomes self-reinforcing, drives rapid deglaciation. The transition from glacial to interglacial happens fast on geological timescales, usually within 5,000 to 10,000 years. That might sound like a long time from a human perspective, but it's remarkably rapid for planetary transformation. Ice sheets miles thick don't melt overnight, but they do melt relatively quickly once the process begins. Sea levels rise hundreds of feet. Coastlines move inland. Climate zones shift. Vegetation patterns completely reorganize. Everything alive must adapt, migrate, or die. The last deglaciation, the one that ended the most recent ice age and brought us into the current warm Holocene period, began about 20,000 years ago and was largely complete by 11,700 years ago. During those 8,000 years, ice sheets that covered North America and northern Europe melted. Sea levels rose about 120 meters. Global temperature increased by 4 to 7 degrees Celsius. It was a planetary transformation, a complete reorganization of climate and ecosystems. And here's what's interesting. Humans lived through that transition. Our ancestors survived the last ice age and watched the world thaw around them. They saw coastlines disappear under rising seas. They saw ice sheets retreat northward. They saw new forests appear in lands that had been frozen tundra. They adapted to fundamentally changing conditions, moving, changing their diets, developing new technologies for new environments. That adaptability, that ability to survive radical environmental change may be one of the key factors in human success as a species. But let's not get ahead of ourselves. Before we talk about humans adapting to ice age endings, we need to understand what life was like during ice ages themselves. What did it mean to live on a frozen planet? How did anything survive when so much of the world was locked in ice? The answer is both bleaker and more interesting than you might expect. Imagine Earth 20,000 years ago, the last glacial maximum, the coldest point of the most recent ice age. Ice sheets cover Canada, northern Europe, parts of Asia. They're not just patches of ice, they're continental-scale glaciers, some over 3 kilometers thick. The weight of the ice depresses the crust beneath, pushing bedrock down into the mantle. When the ice eventually melts, the land will slowly rebound, rising hundreds of meters over thousands of years, a process that's still ongoing in places like Scandinavia and Canada. But it's not just the ice-covered regions that are transformed. Global cooling affects every ecosystem on the planet. Tropical rainforests shrink dramatically. The Amazon is much smaller, fragmented into patches separated by grassland and savanna. African rainforests retreat to tiny refugia in the wettest areas. Coral reefs struggle in cooler waters. Deserts expand because a colder atmosphere holds less moisture, producing less rainfall globally. Much of the planet becomes drier, windier, harsher than during warm periods. Sea levels are 120 meters lower because so much water is locked in ice. This exposes vast areas of continental shelf. The geography is unrecognizable compared to today. The English Channel doesn't exist. You can walk from France to Britain across what's now the North Sea, a land of rivers and forests and grasslands inhabited by mammoths and reindeer. Indonesia is connected to mainland Southeast Asia. New Guinea and Australia are joined. The Bering Strait is dry land, a 1,000-kilometre-wide bridge between Asia and America, where migrations of animals and humans will cross. In the tropics, where no ice exists, life is still profoundly different. Temperatures are 4 to 7 degrees cooler than today. That might not sound like much, but it has enormous effects on ecosystems. Many tropical plants can't reproduce at temperatures much below their current range. Rainfall patterns shift as atmospheric circulation changes. Some regions that are currently wet become much drier. Lake levels in Africa and South America drop dramatically. Some lakes dry up entirely, disappearing until the climate warms again. The animals of Ice Age Earth include species that seem mythological to us now. Woolly mammoths roam the tundra and grasslands, massive herbivores with thick fur and curved tusks adapted to extreme cold. Woolly rhinoceros, equally massive and furry, live alongside them. Giant ground sloths, some weighing several tons, browse vegetation in the Americas. Saber-toothed cats hunt prey that includes young mammoths and giant bison. Cave lions, larger than modern lions, patrol Europe and Asia. Short-faced bears, the largest land predators of the Ice Age, dominate parts of North America. These megafauna, the great Ice Age mammals, thrive in the cold conditions. Many are specifically adapted to glacial climates and will go extinct when the Ice Age ends and the planet warms. Whether humans hunting them contributed to their extinction, or whether climate change alone was responsible, remains hotly debated. Probably both factors played roles, varying by region and species. For humans, life during the Ice Age is incredibly challenging but not impossible. We exist in small bands, perhaps 30 to 100 people in an extended family group. We're nomadic, following game herds as they migrate seasonally. We hunt mammoth and reindeer and bison with spears and traps. We fish in rivers and lakes. We gather whatever plants are edible, which isn't much in the harsh glacial environment. Life expectancy is short. Infant mortality is high. Injury or illness that we'd consider minor today is often fatal, but we survive. We thrive in a way. We develop sophisticated tools, including needles for sewing-fitted clothing, which is essential for surviving extreme cold. We create art, painting magnificent cave paintings in places like Lascaux and Altamira, depicting the animals we hunt and some we don't, images of horses and bison and lions and mysterious abstract symbols that may represent spiritual concepts or astronomical observations. We bury our dead with ceremony, suggesting belief in an afterlife or at least recognition that death is significant and should be marked. We also spread across the globe during the Ice Age. Lower sea levels create land bridges that allow us to reach Australia by 50,000 years ago, and the Americas by 15,000 years ago, or perhaps earlier. The harsh glacial climate doesn't stop human expansion. If anything, it may facilitate it by creating corridors through regions that would be impassable jungle or sea during warm periods. We're an adaptable species, capable of surviving in nearly any environment from tropical islands to Arctic tundra. Different human groups develop different survival strategies for Ice Age life. Some specialize in hunting large game, following mammoth herds across the tundra. Others focus on fishing, settling near productive rivers where salmon run in enormous numbers. Some groups live in coastal areas where the now exposed continental shelf provides rich hunting and gathering. The archaeological record shows tremendous diversity in how different human populations adapt to local conditions. Technology advances during the Ice Age. We develop the atlatl, a spear-throwing device that increases range and force. We create specialized tools for different purposes, scrapers for working hides, burins for carving bone and antler, blades for cutting, points for piercing. We learn to work stone with incredible skill, creating tools that modern flint knappers struggle to replicate. We build sophisticated shelters, sometimes using mammoth bones and tusks as structural elements when wood is scarce. And we form partnerships with other species. Dogs are domesticated during this period, descended from wolves that learned to live near human camps, eventually becoming partners in hunting and guarding. This partnership will prove crucial for human success, providing early warning of predators, assistance in hunting, companionship in the harsh environment. Dogs are our first domesticated species, the beginning of agriculture and animal husbandry that will transform human society when the Ice Age ends. Life during Ice Ages isn't static. The climate varies on shorter timescales too, oscillating between colder and slightly warmer periods within the overall glacial state. These variations, driven by changes in ocean circulation, or volcanic eruptions, or stochastic variation in the climate system, can be dramatic even if they don't rival the full glacial-interglacial transitions. Human populations must constantly adapt, moving as conditions change, developing new strategies for new situations. The end of the Ice Age transforms everything. As the planet warms, ice sheets melt, flooding coastal areas and the land bridges that connected continents. The megafauna begin disappearing. Climate becomes warmer, wetter, more stable. Forests replace tundra. Human populations grow as food becomes more abundant. And, within a few thousand years, agriculture is invented independently in multiple regions. The Neolithic Revolution begins, transforming humans from mobile hunter-gatherers into settled farmers, setting the stage for all of civilization. That brings us to the present and the question that's been lurking throughout this entire story. Are we due for another ice age? Will the ice return on schedule, freezing the planet again in 50,000 or 80,000 years? Or have we broken the cycle through our own activities, pumping so much CO2 into the atmosphere that we've overridden the orbital forcing that would otherwise cool the planet? The answer is complicated. If we look at orbital parameters alone, Earth should be in a long, stable, warm period. The current orbital configuration, with low eccentricity and moderate obliquity, is not particularly favourable for Ice Age initiation. Some models suggest that even without human influence, the next Ice Age might not begin for another 50,000 years. But here's the thing: those models are based on past behaviour, and we've pushed the climate system far outside its recent historical range. Current atmospheric CO2 levels are over 420 parts per million, far higher than the 180 to 280 parts per million range of the past 800,000 years. The warming caused by this CO2, plus other greenhouse gases we've added, has already increased global temperatures by about 1.2 degrees Celsius above pre-industrial levels, and we're on track for more. This warming is happening far faster than the warming that ended the last ice age, and it's happening in the opposite direction from what orbital mechanics would predict. Some scientists argue we've prevented the next ice age entirely through our greenhouse gas emissions. The warming we've caused may persist for thousands of years even if we stopped all emissions today, because CO2 remains in the atmosphere for centuries and because warming oceans and feedbacks maintain elevated temperatures long after emissions cease. We may have inadvertently given ourselves tens of thousands of years of warm climate whether we wanted it or not. Others argue that we haven't fundamentally broken the ice age cycle, just delayed the next one and made the current warm period more intense. Eventually, on timescales of hundreds of thousands of years, orbital forcing will overcome even elevated CO2, and ice will return. But that's so far in the future as to be almost meaningless for thinking about human timescales. The more immediate concern is not ice ages, but the opposite. Rapid warming, climate change driven by human emissions. The feedbacks that amplified orbital forcing during ice ages work in both directions. Melting ice reduces albedo, causing more warming. Warming oceans release dissolved CO2, adding to atmospheric greenhouse gas concentrations. Thawing permafrost releases methane. These feedbacks amplify the warming we're causing, potentially pushing the climate past tipping points into a new stable state, warmer than anything in recent human experience, We don't know exactly how warm it will get or how quickly. That depends on choices we make about emissions over the coming decades. But we do know from studying past climate that Earth is capable of rapid, dramatic change. We know that feedbacks can amplify small forcings into large effects. We know that ice sheets can collapse relatively quickly once melting begins. We know that sea levels can rise meters within centuries during rapid warming periods. The geological record shows all of this has happened before during natural climate variations. What makes our current situation different is the rate of change. Natural climate variations, even rapid ones like the deglaciation that ended the last ice age, took thousands of years. The warming we're causing is happening over decades to centuries. Ecosystems don't have time to migrate. Species can't evolve fast enough to adapt. We've essentially compressed thousands of years of natural climate change into a human lifetime. The consequences are still unfolding, but they're already visible in melting glaciers, rising seas, shifting climate zones, extreme weather events becoming more common. Here's the final twist to this story. The very science that allows us to understand ice ages, that lets us read climate history from ice cores and ocean sediments, that reveals how orbital mechanics drive planetary transformations, this same science tells us with great certainty that we're changing the climate. The physics are the same, the feedbacks are the same, the evidence is equally clear. Deny one and you have to deny the other, because they're built on identical scientific foundations. We're living in the warm window between ice ages, a geological moment when climate is stable enough for agriculture, cities, civilization. That stability is part of what allowed human population to grow from a few million hunter-gatherers to 8 billion people inhabiting every continent we've built, everything we consider modern life during this brief warm period. And now, through our own actions, we're altering the conditions that made that growth possible. Whether this means we've averted the next ice age or simply delayed it while creating different problems doesn't really matter on human timescales. What matters is that we've demonstrated the power to change planetary climate, to alter the composition of the atmosphere, to shift conditions that have governed Earth for hundreds of thousands of years. That's a responsibility our ancestors never had to face. The ice ages teach us that Earth's climate is not static. It changes dramatically on geological timescales. It has tipping points where feedbacks overwhelm initial forcing. It can shift between different stable states. These are lessons we ignore at our peril. We're pushing the climate system in untested directions, activating feedbacks we don't fully understand, potentially crossing thresholds we can't see until we've passed them. But the ice ages also teach us something hopeful. Earth is resilient. Life adapts. Species survive even through dramatic climate changes. Humans made it through the last ice age and the rapid warming that followed. We're resourceful, adaptable, capable of innovation when faced with challenges. The question is whether we'll use those capabilities to mitigate the changes we're causing, or whether we'll simply adapt to whatever climate we create, accepting the costs and consequences. If you're still listening, still drifting towards sleep, thinking about ice and time and planetary cycles, thank you for staying with me through this journey. Ice ages are humbling. They remind us that Earth doesn't exist for our convenience. It follows rhythms older and more powerful than human concerns. We happen to exist during a warm period, a window of unusual stability. But that window is temporary. Either ice will return eventually, or will maintain warmth through our emissions, or will trigger some other climate state entirely. Whatever happens, Earth will continue, life will adapt. The planet has survived far worse than anything humans can do to it. The question isn't whether Earth will be okay in the long run, it's whether we'll be okay, whether we'll maintain a climate compatible with the civilization we've built, whether we'll preserve the conditions that allowed human flourishing. These are choices we're making now, whether we realize it or not. Before you drift off completely, consider subscribing if this resonated with you. Tell me where you're listening from and what time it is where you are. The community around these videos is wonderful. People from around the world falling asleep to science and history and the deep patterns that govern our existence. It's comforting somehow, knowing we're all here thinking about ice ages and orbital mechanics together, connected by curiosity and the desire to understand our place in cosmic timescales. Sleep well, rest deeply, and may your dreams be filled with the strange comfort of knowing that Earth has seen it all before and will see it all again, long after we're gone, cycling between ice and warmth, frozen and green, through eons we can barely comprehend. Good night. The discovery of ice ages didn't happen in a vacuum. It required multiple scientific breakthroughs happening simultaneously across different fields, creating a perfect storm of understanding that transformed how we see Earth's history. In the early 1800s, geology was barely a science. Most people still believed Earth was only a few thousand years old, created exactly as described in Genesis. The idea that landscapes changed over millions of years was heretical, literally. Scientists who proposed ancient ages for Earth risked their careers and reputations, but evidence kept accumulating that couldn't be explained by young Earth models. Fossils of extinct species appeared in rock layers, suggesting life had changed dramatically over time. Mountain ranges showed layers of rock folded and twisted in ways that required immense time to form. River valleys were too large to have been carved by current water flow, implying either much larger ancient rivers or vastly more time than anyone imagined. The evidence demanded new explanations, new frameworks for understanding planetary history. Charles Lyell's Principles of Geology, published in the 1830s, argued for uniformitarianism, the idea that geological processes operating today worked the same way in the past. Mountains rose slowly through countless small earthquakes, rather than in single catastrophic events. Rivers carved valleys grain by grain over millions of years. Continents shifted gradually rather than suddenly. This framework made deep time thinkable, gave scientists permission to imagine Earth's history stretching back far beyond human records or biblical chronology. Into this intellectual revolution came Louis Agassiz with his Ice Age theory. The timing was perfect. Scientists were ready to consider radical ideas about Earth's past. The evidence was visible to anyone who looked, though interpretation required new eyes, new conceptual frameworks. Agassiz provided both the evidence and the framework. He showed that glaciers carved distinctive features. He mapped those features across continents. He proposed ice ages as explanation. And gradually, reluctantly, the scientific community accepted the evidence. But acceptance didn't mean understanding. Scientists knew ice ages happened. They could trace the extent of past glaciations. They could estimate how much ice covered the planet. What they couldn't explain was why. What force caused ice ages to begin and to end? Why did they happen at all? For decades, these questions remained completely mysterious. Theories were proposed and discarded. None fit the evidence. None explained the pattern of repeated glaciations with warm periods between. James Kroll's astronomical theory in the 1860s was the first serious attempt at explanation. Kroll worked as a janitor at Anderson's University in Glasgow because his working-class background prevented academic employment, despite his obvious brilliance. But he read voraciously in the university library, teaching himself mathematics and astronomy and physics. He became obsessed with ice ages after reading about them in a geology textbook. Why did they happen? What caused the pattern? Kroll learned that Earth's orbit wasn't constant. The ellipse varied in shape over time, the axis wobbled. The tilt changed. He obtained astronomical tables showing these variations over hundreds of thousands of years. He taught himself the mathematics to calculate how orbital changes affected solar energy reaching different latitudes. And he proposed a theory. When Earth's orbit was more elliptical, and when that elliptical orbit aligned with the wobble of Earth's axis in certain ways, high-latitude regions received significantly less solar energy during summer. That triggered ice age conditions. Kroll's theory was largely ignored during his lifetime. The mathematics were too complex for most geologists to follow. The astronomical data was difficult to verify, and there was no independent way to test whether ice ages actually correlated with predicted orbital variations. Without some method of dating past ice ages precisely, Kroll's theory remained speculation, however elegant. He died in 1890, his work largely forgotten, remembered only by a few specialists who appreciated its mathematical sophistication, without being able to confirm its predictions. Then came Milutin Milankovic, a Serbian mathematician and engineer born in 1879, brilliant, meticulous, obsessed with precision. He started his career working on concrete and engineering problems, building bridges and dams, but he became fascinated by climate and astronomy. He decided to calculate exactly how Earth's orbital variations affected solar energy at different latitudes through time. The calculations were staggeringly complex. No computers existed. Everything had to be done by hand with tables of logarithms and trigonometric functions. Milankovic spent decades on these calculations. He calculated solar energy at different latitudes for hundreds of thousands of years into the past. He accounted for all three orbital variations, eccentricity, precession, and obliquity, and how they combined and interfered with each other. He created curves showing how summer solar energy varied at high northern latitudes over the past 600,000 years. The work was published in the 1920s and 30s in a series of papers and eventually a comprehensive book. The scientific community was skeptical. Here was another astronomical theory of ice ages, mathematically sophisticated but impossible to test. How could anyone verify that ice ages actually occurred when Milankovic's calculations predicted reduced summer sunlight? The geological dating methods available in the 1930s weren't precise enough to test the theory. Radiocarbon dating wouldn't be developed until the 1940s, and it only works for the past 50,000 years anyway. Methods for dating older materials didn't exist yet. So Milankovic's work sat largely unused for decades. A few scientists studied it. Some found the mathematics compelling. Others rejected it because the forcing seemed too weak to explain observed climate changes. The debate remained unresolved for 40 years after Milankovic's original publications. His theory couldn't be tested, so it remained in limbo, neither confirmed nor refuted, just an interesting mathematical exercise with possible but unproven relevance to real climate. Then came the ice cores. Starting in the 1960s, scientists began drilling into ice sheets in Greenland and Antarctica, extracting cores that preserved climate records going back thousands of years. The early cores were exciting enough, showing climate variations during and after the last ice age. But the real breakthrough came with deeper drilling that recovered ice going back hundreds of thousands of years. The GIS P2 core from Greenland reached back 110,000 years. The Vostok core from Antarctica reached 420,000 years. Later, the Epica cores from Antarctica extended the record to 800,000 years. These ice cores could be dated by counting annual layers in the younger sections, like counting tree rings. Deeper sections required more sophisticated techniques, using mathematical models of ice flow and dating tie points from volcanic ash layers or other markers. But the result was detailed climate chronologies going back further than any previous record. And crucially, these chronologies could be compared to astronomical calculations of orbital variations. The comparison was striking. Ice ages occurred when Milankovic's calculations showed reduced summer solar energy at high northern latitudes. The timing matched too precisely to be coincidence. The dominant cycle in the ice core data was roughly 100,000 years, matching the eccentricity cycle. Earlier ice ages followed a 41,000-year pattern, matching the obliquity cycle. The correlation confirmed Milankovic's theory. Orbital variations do drive ice ages, but the ice cores revealed something Milankovic never predicted. Carbon dioxide levels varied in lockstep with temperature. During glacial periods, CO2 dropped to about 180 parts per million. During interglacials, it rose to about 280 parts per million. The correlation was nearly perfect across hundreds of thousands of years. This was completely unexpected. Milankovic's theory involved only orbital mechanics and solar energy. He didn't consider atmospheric chemistry or greenhouse gases because nobody in the 1920s understood their climate importance. The discovery of CO2 variations in ice cores transformed understanding of ice ages. It wasn't just orbital forcing. It was orbital forcing amplified by greenhouse gas feedbacks. The small temperature changes caused by orbital variations triggered changes in CO2 levels through ocean chemistry and other mechanisms. Those CO2 changes amplified the warming or cooling, creating the full Ice Age cycles. The theory became more complex but also more complete, explaining observations that pure orbital theory couldn't account for. Ocean sediment cores provided another crucial line of evidence. Starting in the 1960s, oceanographers began systematic programs of drilling into the ocean floor, extracting cores of sediment that recorded ocean history going back millions of years. The Deep-Sea Drilling Project, later renamed the Ocean Drilling Program, collected thousands of cores from all ocean basins, creating an archive of Earth history unmatched by any land-based record. These ocean sediments contain shells of foraminifera, tiny single-celled organisms that live in the ocean and build calcium carbonate shells. When the organisms die, their shells sink to the seafloor and accumulate in layers. The chemistry of those shells records ocean temperature and ice volume. Specifically, the ratio of oxygen isotopes in the shells changes based on temperature and how much of Earth's water is locked in ice sheets. By analysing shells from different depths in sediment cores, scientists reconstruct ocean temperature and ice volume going back millions of years. The ocean sediment records confirmed and extended what ice cores showed. Ice ages occurred regularly for at least the past 2.6 million years, the entire Pleistocene epoch. Before that, Earth was generally warmer with much less ice. The transition into the current Ice Age regime happened gradually between 3 and 2.6 million years ago, as global temperatures cooled enough that ice sheets could form and persist in the northern hemisphere. Once ice began accumulating, the orbital forcing that Milankovitch calculated started driving regular cycles of glaciation and deglaciation. The ocean records also showed the mid-Pleistocene transition clearly. Before about 1.2 million years ago, ice ages followed a 41,000-year cycle. After the transition, they followed a 100,000-year cycle. The change wasn't gradual. It happened over several cycles, suggesting some threshold was crossed where the climate system's response to orbital forcing fundamentally changed. Understanding this transition remains one of the great challenges in paleoclimate science. Multiple lines of evidence converged in the 1970s and 80s to create a comprehensive understanding of ice ages. Ice cores provided direct measurements of temperature and CO2. Ocean sediments showed the global pattern and extended the record back millions of years. Dating methods improved dramatically with developments in radiometric techniques, allowing precise age determination for samples from hundreds of thousands of years ago. Computer models became sophisticated enough to simulate climate under Ice Age conditions and test theories about ice sheet dynamics and climate feedbacks. The result was one of the great scientific syntheses of the 20th century. The mystery that stumped scientists since Agassiz first proposed ice ages in 1837 was finally solved. Not completely, not every detail, but the broad outline was clear and well supported by multiple independent lines of evidence. Ice ages are driven by orbital variations that change the distribution of solar energy on Earth's surface. Those small changes are amplified by feedbacks involving ice albedo, greenhouse gases, ocean circulation, and vegetation. The result is dramatic climate changes that transform the planet repeatedly on 100,000-year timescales. But understanding the mechanism raised new questions. Could we predict future ice ages? Should we worry about the next glaciation? Or has human activity altered the climate so much that the natural cycle is broken? These questions remain hotly debated. Some scientists calculate that without human influence, the next ice age wouldn't begin for 50,000 years based on current orbital parameters. Others argue that we're right at the edge of conditions favourable for glaciation, and only our greenhouse gas emissions are preventing ice sheets from expanding. The debate matters because it speaks to our impact on planetary systems. If we've prevented an ice age through our emissions, that's a profound demonstration of human power to alter global climate. If we're simply delaying the inevitable, that's still significant, but less dramatic. Either way, the fact that we can discuss preventing ice ages shows how far our influence has grown. We've become a geological force, capable of shifting Earth's climate in ways that will be visible in ice cores and ocean sediments millions of years from now. The study of ice ages also transformed how scientists think about climate stability. Before Ice Age research, many scientists assumed climate was relatively stable, unless perturbed by rare catastrophic events. The ice core and ocean records showed that assumption was wrong. Climate varies dramatically on multiple timescales, from decades to hundreds of thousands of years. Ice ages themselves show that Earth can exist in radically different stable states, flipping between them based on relatively small changes in forcing. This discovery of climate instability has profound implications for understanding modern climate change. If small variations in orbital parameters can trigger ice ages through feedbacks, what will happen when we push greenhouse gas levels far above anything seen in the past million years? The feedbacks that amplify orbital forcing work in both directions. Warming triggered by our emissions will be amplified by melting ice, rising CO2 from warming oceans, thawing permafrost releasing methane. The full extent of warming won't be limited to the direct effect of our emissions. It will include all the feedbacks our emissions trigger. The geological record shows these feedbacks are real and powerful. During past warm periods, even modest increases in temperature triggered positive feedbacks that amplified warming beyond the initial cause. During the Eemian interglacial 125,000 years ago, temperatures only slightly warmer than today caused ice sheet collapse and sea level rise of 6 to 9 meters. That's the kind of amplification we should expect from current warming. The question isn't whether feedbacks will amplify our forcing. The question is how much and how fast. Scientists studying ice ages have also discovered how quickly climate can change. For decades, the assumption was that major climate shifts take thousands of years, giving ecosystems and species time to adapt and migrate. Ice cores from Greenland shattered that assumption. They show that during the last ice age, temperature in Greenland sometimes changed by 10 to 15 degrees Celsius within a few decades. These abrupt climate changes, called Dansgaard-Oeschger events after their discoverers, happened repeatedly during glacial periods. The mechanism appears to involve ocean circulation in the North Atlantic. Changes in the strength of the Gulf Stream and deep water formation can flip the North Atlantic between different stable states, warm and cold, with temperature differences of many degrees. These flips happen rapidly, within years to decades, not millennia. The entire climate system of the Northern Hemisphere reorganizes in response. The discovery of abrupt climate changes showed that Earth's climate can shift dramatically on timescales shorter than human civilization. That's deeply concerning when we're pushing the climate system with unprecedented forcing. The story of discovering ice ages is a story of scientific method working exactly as it should. Observations that didn't fit existing theories led to new hypotheses. Those hypotheses were tested against additional evidence. Multiple independent lines of investigation converged on the same conclusions. Mathematics from astronomy connected to chemistry from ice cores connected to biology from ocean sediments. The result was comprehensive understanding built on interlocking evidence from diverse fields. It's also a story of perseverance. Agassiz faced ridicule for proposing ice ages. Kroll worked as a janitor while developing brilliant astronomical theories that were ignored during his lifetime. Milankovitch spent decades on calculations that weren't confirmed until 40 years after he published them. Scientists drilling ice cores and ocean sediments faced enormous technical challenges and often skeptical funding agencies, but they persisted because the questions mattered and the evidence demanded explanation. Now we have detailed understanding of how ice ages work. We can read climate records going back 800,000 years in ice cores, millions of years in ocean sediments. We can calculate orbital variations with extraordinary precision. We can model the physics of ice sheets and ocean circulation and atmospheric chemistry. We can predict how climate responds to different forcings. This knowledge didn't come easily. It required brilliant scientists working across multiple disciplines for over a century. But it gives us tools to understand our current situation and what we're doing to planetary climate. The ice ages teach us that Earth's climate is sensitive to small changes in forcing, that feedback loops can amplify those changes dramatically, that the climate system has tipping points where it shifts between different stable states, that changes we thought would take thousands of years can happen in decades. These lessons should inform how we think about modern climate change. We're not just adding a bit of CO2 to the atmosphere, We're pushing a sensitive, nonlinear system with known feedback amplification. The geological record shows clearly what happens when you do that. The climate changes, dramatically, sometimes abruptly, often in ways that transform ecosystems and force species to adapt or die. Living through the discovery of ice ages must have been intellectually thrilling. Imagine being a geologist in the late 1800s, watching the evidence accumulate, seeing the pattern emerge from scattered observations. Imagine being one of the scientists drilling the first deep ice cores, seeing climate records appear from ice that fell as snow hundreds of thousands of years ago. Imagine running the first calculations comparing Milankovitch's orbital theory to ice core chronologies and seeing them match. Those moments of discovery, when mystery becomes understanding, are what science is all about. We're living through our own moment of discovery now, learning how climate responds to unprecedented greenhouse gas levels, watching feedbacks activate in real time, seeing predictions from climate models verified by observations. Future generations will look back on this period the way we look back on Ice Age discoveries. They'll see us learning, understanding, grappling with planetary transformation driven by our own activities. Whether they'll see us acting on that understanding or ignoring it remains to be written. But for now, as you drift towards sleep, consider the deep time perspective that Ice Age research provides. The planet has been through dramatic changes before. Ice has advanced and retreated dozens of times. Life has adapted through all of it. Species have gone extinct and new ones have evolved. Earth continues regardless of whether any particular species survives. That's both humbling and oddly comforting. We matter, but we're not the centre of planetary history. We're just one species living during one brief interglacial, trying to understand the cosmic forces that shape our world. Sleep well with that knowledge. Rest in the comfort of deep time and planetary endurance. The scientific understanding of ice ages represents one of humanity's great intellectual achievements. From complete ignorance to detailed knowledge in less than 2 centuries demonstrates what systematic investigation and collaborative science can accomplish. Multiple disciplines contributed essential pieces. Geology provided evidence of past glaciations. Astronomy calculated orbital variations. Physics and chemistry developed isotope analysis techniques. Engineering created drilling technology. Mathematics built models connecting observations to theory. Computer science enabled simulations too complex for hand calculation. No single person could have solved the Ice Age mystery alone. It required collaboration across generations, with later scientists building on foundations laid by predecessors. Agassiz couldn't have proposed ice ages without geological knowledge accumulated through the early 1800s. Kroll couldn't have calculated orbital effects without astronomical data collected over centuries. Milankovitch couldn't have completed his computations without mathematical methods developed by earlier mathematicians. Ice core scientists couldn't have extracted climate records without drilling technology developed for other purposes. The synthesis required all these pieces coming together. This collaborative nature of science often gets lost in popular accounts that focus on individual genius. While brilliant individuals certainly contributed crucial insights, the overall progress depended on communities of scientists working together, sharing data, critiquing each other's work, building consensus around well-supported ideas while discarding those that didn't fit evidence. This process can be slow and frustrating, but ultimately produces reliable knowledge. The story of Ice Age discovery also shows how science changes our view of Earth and humanity's place in time. Before Ice Age research, most people saw Earth as essentially unchanging except for rare catastrophes. Mountains and valleys had always been there. Coastlines were permanent. Climate was stable. This view fit with religious teachings about divine creation and gave humans a sense of centrality and importance. Ice Age research shattered that comfortable view. Earth has history, dramatic history. The landscape constantly changes over geological time. Coastlines shift by hundreds of miles as ice builds and melts. Climate oscillates between radically different states. Nothing is permanent on geological timescales. This realization was initially disturbing for many people. It meant humans weren't living in a world designed specifically for them, but in a dynamic planet that happened to be in a state suitable for human life at this particular moment. But the discovery also revealed something wonderful. Understanding ice ages showed that nature operates according to comprehensible laws. The cycles aren't random chaos, but responses to calculable forcing. We can understand why climate changes, predict how it will change, and potentially even influence those changes. This knowledge is empowering even as it's humbling. We're small in geological time but capable of understanding forces vastly larger than ourselves. The methods, developed to study ice ages, now apply to other planetary questions. The same techniques used to analyze ice cores work on rock cores from ocean floors or lake beds. The same orbital mechanics that explain ice age timing help explain climate variations on Mars or the moons of outer planets. The same climate models used to simulate ice ages help predict future climate change. Science builds tools and methods that prove useful far beyond their original applications. Looking forward, ice age research continues evolving. Drilling projects seek even older ice, perhaps reaching back 1.5 million years to the mid-Pleistocene transition. Ocean drilling programs core sediments from regions not previously sampled, filling gaps in global coverage. Improved climate models tackle remaining puzzles about feedback strength and tipping point locations. Satellite measurements monitor current ice sheet changes, testing whether models correctly predict ice dynamics. One fascinating frontier involves studying ice ages on early Earth. The first ice ages occurred over 2 billion years ago during the Huronian glaciation. Evidence suggests ice reached tropical latitudes, possibly covering the entire planet in a snowball Earth scenario. Later, between 720 and 580 million years ago, several severe glaciations may have frozen Earth globally. These ancient ice ages operated differently from recent ones because Earth's atmosphere and biology were vastly different. Understanding them requires developing new models and finding new types of evidence. Another research direction examines how life influenced ice ages. Plants draw down CO2 through photosynthesis. Certain types of rock weathering are enhanced by plant roots and soil organisms. The rise of land plants around 400 million years ago may have contributed to ice ages by reducing atmospheric CO2. Later evolution of different plant types with different effects on carbon cycling may have influenced ice age intensity. Life doesn't just respond to climate, it shapes climate, creating feedbacks that affect planetary conditions. The interaction between life and climate becomes especially important when considering modern changes. Humans have altered land cover globally through agriculture and urbanization. We've changed atmospheric composition through emissions. We've modified ecosystems through extinction and introduction of species. All these activities affect climate directly and through feedbacks. Understanding natural climate-life interactions helps predict how our modifications will propagate through the system. Some scientists propose geoengineering schemes to counteract warming we've caused. Ideas include injecting sulfate aerosols into the stratosphere to reflect sunlight, brightening marine clouds to increase albedo, removing CO2 from the atmosphere through direct air capture, or enhanced weathering. These schemes remain largely theoretical but are being seriously researched. They raise profound questions about deliberately manipulating planetary climate systems we don't fully understand. The Ice Age Record Council's caution with such schemes. When we look at abrupt climate changes in the past, we see that climate system responses to forcing aren't always proportional or predictable. Relatively small forcing sometimes trigger large responses through feedbacks. Tipping points exist where climate flips from one state to another. Deliberately adding another forcing to counteract warming from greenhouse gases might work smoothly, or might trigger unexpected responses. On the other hand, we're already geoengineering through our emissions. We're not consciously designing the outcome, but we're definitely changing the system. The question isn't whether to influence climate, but how to influence it more thoughtfully. The Ice Age record provides both warning and guidance. Warning about feedbacks and tipping points. Guidance about which forcings have how much effect on timescales we care about. As you drift fully towards sleep now, carry with you the deep time perspective that Ice Age research provides. The ice has advanced and retreated dozens of times. Life has survived through all of it. Earth endures. Whatever changes we cause, whatever happens to human civilization, the planet itself will continue cycling through its patterns on timescales that dwarf human concerns. There's comfort in that cosmic perspective. We matter, but we're not the centre of everything. We're participants in a story vastly larger than ourselves. Sleep well in that knowledge. Rest deeply in the embrace of geological time. Good night, and may your dreams be peaceful as the ice between glaciations. The patterns we see in Ice Age records reveal something profound about how Earth's climate operates. The system has memory. What happened in previous cycles affects how the planet responds to current forcing. Ice sheets don't instantly appear or disappear. They build gradually over thousands of years, growing as each winter's snow fails to fully melt. Once established, they create their own climate, reflecting sunlight, cooling the surrounding atmosphere, altering wind patterns. Breaking out of a glacial state requires substantial forcing, because the ice resists melting through feedback mechanisms that reinforce cooling. This hysteresis, the technical term for systems that resist change once they've settled into a state, helps explain why ice ages last so long compared to the relatively brief warm periods. Getting into a glacial state is gradual, responding to slowly declining orbital forcing over tens of thousands of years. Getting out requires crossing a threshold where warming feedbacks overcome the stabilizing effects of ice and low CO2. Once that threshold is crossed, the transition happens relatively quickly, within a few thousand years rather than tens of thousands. Modern climate science borrows heavily from techniques developed to study ice ages. Climate models began as simplified representations of atmospheric circulation and energy balance. Early models could barely simulate seasonal changes, let alone ice ages. But as computing power increased and scientific understanding deepened, models incorporated more physics, ocean circulation, sea ice formation, cloud dynamics, vegetation changes, carbon cycle feedbacks. Modern Earth system models simulate all these processes simultaneously, creating virtual planets that behave remarkably like the real Earth. Testing these models against Ice Age data provides crucial validation. If a model can reproduce the timing and magnitude of past ice ages when forced with known orbital variations, that gives confidence the physics is correct. If it fails, that reveals gaps in understanding that need to be addressed. The ice ages provide a natural laboratory for testing climate science, offering climate changes far larger than anything in the instrumental record, driven by well-understood forcing with outcomes preserved in multiple independent archives. This testing has revealed both successes and failures. Models successfully reproduce the broad pattern of ice ages, the dominant 100,000-year cycle, the correlation with orbital forcing. They capture feedback amplification through ice albedo and CO2 changes. They simulate abrupt climate changes like those seen in Greenland ice cores, but they struggle with some details. The exact timing of deglaciations doesn't always match observations perfectly. The magnitude of temperature change varies between models and observations. Some regional climate features don't reproduce well. These discrepancies drive ongoing research. When models disagree with data, either the model physics needs improvement or the data interpretation needs revision. Often, it's some of both. Data from hundreds of thousands of years ago always involves interpretation and uncertainty. Proxy measurements don't directly record temperature but rather quantities that correlate with temperature. Ice core isotopes, from shell chemistry, pollen assemblages, all require calibration and assumptions. Similarly, models make assumptions about processes they can't fully resolve, parameterizing small-scale physics with simplified equations. The dialogue between models and data, each informing the other, gradually improves both. Better data constrains models, showing which parameterizations work and which don't. Better models suggest new questions to ask of data, new proxies to develop, new archives to sample. The result is steadily improving understanding of how ice ages work and what they reveal about climate system behavior. One fascinating aspect of recent ice age research involves the role of dust. During glacial periods, atmospheric dust levels were dramatically higher than today. Ice cores preserve this dust, tiny particles of mineral matter blown from exposed continental shelves and arid interiors. The dust isn't just a passive marker of dry, windy conditions, likely played an active role in climate through multiple mechanisms. Dust in the atmosphere reflects sunlight, creating a cooling effect. Dust deposited on ice sheets darkens the surface, reducing albedo and enhancing melting. Dust falling into oceans provides iron, a nutrient that limits plankton growth in many regions. More iron means more plankton, which draws down atmospheric CO2 through photosynthesis. When plankton die and sink, they carry carbon to the deep ocean, removing it from the carbon cycle for centuries. This iron fertilization mechanism may help explain part of the CO2 drawdown during ice ages. Recent experiments have tested iron fertilization directly by dumping iron compounds into iron-limited ocean regions and measuring the response. Phytoplankton blooms develop, proving that iron is indeed limiting in these areas. Whether the blooms sequester carbon long-term is more complicated, depending on whether the organic matter sinks before being consumed by bacteria and respired back to CO2. But the mechanism is plausible and supported by evidence from Ice Age dust records. Another active research area involves Antarctica's role in Ice Age cycles. The southern hemisphere has less land than the northern hemisphere, so ice sheet growth is limited to Antarctica, which already has a permanent ice sheet. But Antarctica's ice can still expand and contract, influencing global sea level and climate. During glacial periods, Antarctic ice extended further onto the continental shelf as sea level dropped. The expanded ice sheet altered ocean circulation around Antarctica, affecting heat transport and carbon storage in the Southern Ocean. Some scientists propose that changes in Antarctic ice and Southern Ocean circulation may actually lead Northern Hemisphere ice sheet changes, rather than simply responding to them. The idea is that Southern Ocean processes control atmospheric CO2 by regulating carbon exchange between the ocean and atmosphere. When CO2 drops, global cooling begins, eventually triggering Northern Hemisphere ice sheet growth. This would make Antarctica the pacemaker of ice ages, with orbital forcing acting primarily through Southern Hemisphere processes. The hypothesis remains controversial and actively debated. Some data supports it, showing Antarctic temperature changes leading Northern Hemisphere changes by a few centuries. Other data suggests the relationship is more complex, with feedbacks operating in both directions. Resolving this question requires better understanding of Southern Ocean physics and better dating of Antarctic ice core records relative to Northern Hemisphere climate proxies. Regardless of whether Antarctica leads or follows, the Southern Ocean clearly plays a crucial role in ice age cycles. The ocean surrounding Antarctica is the only place where surface water sinks to the deep ocean without travelling thousands of miles through other basins first. This Antarctic bottom water formation is a key component of global ocean circulation. Changes in the process affect how carbon and heat distribute through the deep ocean, influencing climate globally on timescales from decades to millennia. Modern observations show Antarctic bottom water formation is changing. The water is getting warmer and less dense. The rate of formation may be declining. If this continues, it could weaken global ocean circulation, alter carbon storage, affect climate in ways we're only beginning to understand. The changes are likely related to warming and ice loss in Antarctica, demonstrating how modern climate change is affecting processes that govern ice age cycles. The study of ice ages also reveals the importance of sea ice, frozen ocean surface that expands dramatically during glacial periods. Sea ice differs from land ice in important ways. It's thinner, typically only a few meters compared to kilometers for ice sheets. It forms and melts much more quickly, expanding in winter and contracting in summer. It's more mobile, drifting with winds and currents. But despite these differences, sea ice exerts powerful influence on climate through its high albedo and its insulation of the ocean from the atmosphere. During ice ages, sea ice extended far beyond its current limits. In the North Atlantic, winter sea ice may have reached as far south as the latitude of France. In the Southern Ocean, it expanded hundreds of kilometers further north. This additional sea ice reflected more sunlight, contributing to cooling. It also prevented heat exchange between ocean and atmosphere, keeping polar regions extremely cold. Models suggest sea ice feedbacks are important for sustaining ice age conditions, though less important than ice sheet and CO2 feedbacks. Modern Arctic sea ice is disappearing far faster than models predicted just 2 decades ago. Summer minimum extent has decreased by about 40% since satellite observations began in 1979. The ice is younger and thinner, more vulnerable to melting. Some models project ice-free Arctic summers within decades. This rapid change is both consequence and cause of warming. Less ice means less albedo, means more absorbed sunlight, means more warming, means less ice. The feedback is operating in reverse compared to ice ages, amplifying warming instead of cooling. Watching Arctic ice disappear in real time provides unsettling confirmation of feedback, amplification that ice age research revealed. Small forcing, in this case greenhouse gas warming, triggers ice loss. Ice loss amplifies the forcing through albedo feedback. The amplification accelerates the change beyond what the original forcing alone would produce. We're seeing the ice age mechanisms operate in fast forward, driven by human emissions instead of orbital variations. The ice age record also teaches lessons about how species respond to climate change. During glaciations, species didn't go extinct because climate got colder. They went extinct because they couldn't migrate fast enough to track suitable climate zones as those zones shifted. Mammals, being mobile, generally survived by moving. Plants, slower to migrate, often got trapped in unsuitable regions. Only those near climate refugia, small areas that maintained suitable conditions, could persist. Looking at where species survived the last ice age reveals the importance of refugia. In North America, many tree species retreated to the southeastern United States and Mexico. In Europe, the Alps and Mediterranean regions served as refugia. After the ice retreated, species spread back northward from these refuges, recolonizing areas that had been under ice or tundra. Genetic studies of modern populations can trace these migrations, identifying which refugia gave rise to which present-day populations. But recolonization took millennia. Forests didn't instantly appear as ice retreated. Tree species migrated north at different rates, limited by how fast they could disperse seeds and how long it took new seedlings to mature and produce their own seeds. Estimates suggest migration rates of perhaps hundreds of meters per year for slow-dispersing species. Given that climate zones shifted northward by thousands of kilometers as the ice melted, full recolonization took 5,000 to 10,000 years. Modern climate change is happening far faster than past natural changes. Climate zones are shifting poleward at rates of kilometers per decade. Tree species cannot migrate that fast. They're stuck in increasingly unsuitable climates, dying from heat stress and drought before they can be replaced by better adapted species from the south. We're creating a situation where species cannot keep up with climate change through migration alone. Extinction becomes likely unless we actively help species move through assisted migration programs, or unless they can adapt through evolution, which seems unlikely given the speed of change. The megafauna extinctions at the end of the last ice age provide a preview of what happens when climate change outpaces species' ability to adapt. Large mammals that specialized on glacial environments died out when those environments disappeared. They couldn't evolve fast enough to adapt to warming conditions. Their specialized adaptations became liabilities. The lesson is clear. Rapid climate change causes extinctions, especially of large, slow-reproducing specialists. We're likely creating another extinction pulse through the rapid warming we're causing, comparable to the end-Pleistocene extinctions or worse. As you drift towards sleep, thinking about ice and time and planetary rhythms, remember that we're part of this story now. We're not separate observers studying Earth's history from outside. We're participants, active agents changing the climate in ways that will echo through geological time. The ice age cycles may be ending, disrupted by our emissions, or they may simply be delayed, waiting to resume once CO2 levels eventually decline. Either way, we've demonstrated that humans can alter planetary climate, that our species has become a geological force. What we do with that power remains to be seen. Sleep well, and may your dreams be peaceful as falling snow. Good night. The relationship between ice ages and evolution goes deeper than simple extinction and survival. Climate oscillations drove evolutionary innovation by creating fluctuating selection pressures. Species that could adapt to varying conditions had advantages over specialists locked into narrow niches. This may explain why humans, with our remarkable behavioural flexibility, evolved during the Pleistocene Ice Age cycles. Our ancestors faced constantly changing climates across Africa and Eurasia. Those who could innovate, who could develop new tools and strategies for new conditions, survived and reproduced. Those locked into rigid behaviours died out. Some anthropologists argue that Ice Age climate instability was crucial for human evolution. The rapid environmental changes, especially in East Africa where human evolution was centred, created powerful selection pressure for intelligence and adaptability. Brains are metabolically expensive, requiring enormous amounts of energy. They only evolve when the benefits outweigh the costs. In stable environments, fixed behaviours programmed by instinct work fine. In rapidly changing environments, the ability to figure out novel solutions to new problems becomes valuable enough to justify the cost of large brains. The archaeological record supports this view. Stone tool technology became more sophisticated during periods of climate instability. Art and symbolic behaviour emerged during particularly volatile climate periods. The greatest innovations in human technology correlate with the most dramatic climate shifts. This doesn't prove that climate change caused these innovations, but it's consistent with the idea that environmental challenge drove cognitive evolution. Modern humans emerged around 300,000 years ago during a period of extreme climate variability. We spread out of Africa and across the world during the last glacial period, adapting to environments ranging from tropical rainforest to Arctic tundra. Our success came from behavioural flexibility rather than physical adaptation. We could survive anywhere by inventing appropriate technologies and social structures. That flexibility is our inheritance from Ice Age climate instability. But that same flexibility may be creating problems now. We're so good at adapting to local conditions that we've buffered ourselves from immediate climate impacts. Air conditioning, heating, irrigation, global food distribution all allow us to maintain comfortable lives despite changing conditions. This buffering means we don't feel urgent need to address climate change until impacts become severe. By then, we're committed to additional change from past emissions. Our evolutionary success at adapting to climate instability may hinder our ability to recognise and respond to the climate instability we're creating. The Ice Age record also reveals the importance of thresholds and tipping points in climate. The transition from glacial to interglacial doesn't happen smoothly and gradually. It involves abrupt changes where the system flips from one state to another. These transitions likely involve crossing thresholds where feedbacks shift from stabilising to destabilising. Below the threshold, the system resists change. Above it, change accelerates. Modern climate change may be approaching similar thresholds. The Greenland and West Antarctic ice sheets may have tipping points beyond which collapse becomes inevitable, even if we stopped warming. Permafrost thawing may cross thresholds where carbon release becomes self-perpetuating. Ocean circulation may have critical points where relatively small additional warming triggers dramatic reorganisation. We don't know exactly where these thresholds are because we've never pushed the climate system this far this fast before. The precautionary principle suggests we should avoid finding out where tipping points are through uncontrolled experimentation. Once crossed, thresholds may be impossible to reverse on human timescales. We can't unmelt ice sheets or refreeze permafrost or restore ocean circulation once we've disrupted it beyond recovery. The Ice Age record shows that Earth eventually recovers from dramatic climate changes, but eventually means thousands to tens of thousands of years. That's no comfort to civilization trying to function during the transition. Studying ice ages also reveals the interconnectedness of Earth's climate system. Changes in Arctic ice affect tropical rainfall. Changes in tropical vegetation affect polar temperatures through atmospheric circulation and greenhouse gases. Changes in ocean circulation affect weather patterns globally. Everything connects to everything else through complex feedbacks operating on different timescales. This interconnectedness means you can't change one part of the system without affecting others, often in unexpected ways. This lesson applies directly to modern climate change. Greenhouse gas emissions don't just cause uniform warming, they alter precipitation patterns, shift storm tracks, change ocean currents, affect vegetation distributions, modify ice sheet stability. All these changes feed back on each other, creating cascading effects that models struggle to predict in detail. We're not just making the planet warmer, we're reorganizing the entire climate system in ways that will take centuries to fully manifest. The geological perspective that Ice Age research provides is both humbling and empowering. Humbling because it shows how small we are in geological time, how brief our civilization is compared to the timescales on which ice ages operate. The entire span of human civilization, from the first cities to today, fits comfortably within a single warm interglacial period. We've never experienced Ice Age conditions as a civilized species. Our entire understanding of agriculture, architecture, settlement patterns, trade routes, all developed during unusual climate stability. But the perspective is also empowering because it shows we can understand these vast processes. We're not helpless before incomprehensible forces. We've figured out why ice ages happen. We can read climate records going back hundreds of thousands of years. We can predict how orbital variations will affect future climate. That knowledge gives us ability to make informed choices about our own climate impacts. We're not passengers on a planet doing things to us. We're drivers with hands on the wheel, for better or worse. The question facing us now is what we do with this knowledge and power. Do we continue altering climate without regard for consequences, trusting that technology will solve any problems we create? Do we attempt to reverse the changes we've already made through aggressive emissions reductions and carbon removal? Do we adapt to whatever climate we create, accepting losses and moving forward? There's no obvious right answer because the timescales are so long and the uncertainties so large. What's clear from Ice Age research is that climate can change dramatically, that feedbacks amplify small changes into large ones, that tipping points exist, that the changes we're causing are unprecedented in recent geological time. These facts don't dictate specific policies, but they constrain what's plausible. We can't pretend climate is stable or that our emissions don't matter. The Ice Age record proves climate changes profoundly, and that relatively small forcings can trigger those changes through feedback amplification. As you finally surrender to sleep, drifting away from ice and time and planetary cycles, carry this thought. We're living in a unique moment. The brief, warm window between ice ages that allowed civilization to flourish. The moment when one species gained enough knowledge and power to alter planetary climate. The junction point where natural cycles that governed Earth for millions of years encounter human influence, unprecedented in scale and speed. What happens next is being decided now by choices we make about energy, development, technology, values. The ice will remember. Future cores drilled from Antarctic ice 1 million years from now will preserve chemical traces of what we did in this century. Our fingerprints will be visible in the geological record forever. Sleep well with that responsibility. Rest in the knowledge that you're part of this story, living through a pivot point in Earth's history. Good night, and may your dreams be filled with the ice and stars and deep time stretching endlessly in all directions. The planet endures.